Okay, so now what we're going to do is talk about capacitance. And capacitance is the ability to store charge. Okay, so it's the, if you want to think of it, it's the capacity to store charge for a given potential difference. And what that means is at a certain voltage, it will have a certain amount of charge. If it has a certain capacitance, we measure that in farads. Whoa, but we got to spell it correctly. Farads, F-A-R-A-D-S. Farads. And the symbol for capacitance is C. And charge per given voltage. And so the equation for this is C equals Q over V, charge per unit voltage, coulombs per volts, or farads. And the reason you might use capacitance, the reason we want to know something about capacitance, is because sometimes we want to be able to store charge that could be released quickly. Capacitors can release charge quickly. If this is a battery, and I'm not going to get into circuit symbols yet, but okay, plus and minus. If we charge up a capacitor, and that's the symbol for a capacitor right there, if we charge it up, it has the same voltage. Let's just say that's a 9-volt battery. There'd be 9 volts across this. The big difference is if you take a 9-volt battery and you try to light a light with it, yeah, it'll light a bulb for a little bit, but for some circumstances, like think of a flash on a camera, you want a whole lot of charge to move very quickly, and the battery just can't move it that fast. It can't generate that much charge that quickly. So we could just load up charge on a capacitor, and boom, you know, when you connect that to the bulb, all that charge will go through very fast. Another thing we use capacitors for is in circuits. We could say a capacitor has a time-dependent profile, and you can use this for things where you want to change applications where you want to change the time dependence of certain things. An example of this is radio. If you think of AM radio, it's a signal like this, a carrier, that you make bigger or smaller depending on whether you want that sound louder or softer. So it could look like something like this. Okay, and this carrier is just, you know, this would be, the frequency of the carrier would be, you know, 580 kilohertz or 1060 kilohertz. And this carries the signal. What we want, we don't necessarily want to see this. We want this, which would be, this envelope would be the sound. And we want to get rid of this carrier. And one of the ways we can do this is by a combination of resistors and capacitors that would eliminate this specific frequency. So when you tune a radio, it's actually tuning a capacitive circuit that removes these things. And there are more applications. Another reason we might want to know about capacitance is because capacitance, just as we can find it helpful, it can be hurtful. If you have capacitance in a circuit, it can change the results from what you want. And capacitance, every object in the world has some, every metallic object has some degree of capacitance. So we want to understand these things so we can minimize the bad capacitance, if you want to put it that way, or we can plan for the capacitance. Okay, so let's talk a little bit more about what's involved. I've been going on and on about capacitors. Okay, the traditional type of capacitor is a parallel plate capacitor. Think of a plate there and a plate here, going three-dimensional here. There we go. So there's a plate, and this will have a positive charge Q, and this other one will have a negative charge Q, and they're separated by some distance. And this parallel plate capacitor, when we talk about this charge C equals Q over V, When we talk about that charge, we only talk about one of those charges. When we talk about the voltage, the delta V between those two plates. So the delta V between these two plates, okay? But we don't have to count this charge and that charge. That would be 0, of course, so we just count the magnitude of one over the other. And you'll see this, where in capacitors we tend to view this, the positive charge and an equal negative charge on the other side. So let's continue on with this. I want to point out something about electric fields in a capacitor, or something like this. Okay, that would be connected to a circuit somewhere. If we have positive charges all along here, in fact, I don't want to write that because it's going to get too sloppy. This gets busy. Here's a positive charge, here's a negative charge. Okay, from a positive charge, if we draw the E fields, they would be going out in all directions. Okay, I shouldn't say in all directions. They'd be going out up and down in both directions. Okay, and let me draw a little arrow there. So in other words, the E fields go out from the positive plate. So if there's no negative plate here, this is what the field lines would look like. Okay, if there's a negative plate, I'm going to use a different color that hopefully works. That's too bright. That's crazy. Okay, and here's red. Okay, from the negative plate, it goes into the negative plate. Okay, so if there's only a negative plate, the E fields would look like this. Okay, the result of all that is, you can see here, these cancel out somewhat. So outside the capacitor, the electric fields cancel. Inside they add, and of course it's not perfect, but if it's a small distance, then the electric fields outside the capacitor won't matter that much. Inside, the electric fields will be twice as big. They will add together. So if we look at a parallel plate capacitor, and let me move this down, we only care about the charges, about the electric field in the middle there. And the electric field, let's do plus Q. If we do Gauss's law with a symmetric cylinder above and below, and there's A, and here's, I better draw this like this, here's my A right there where it intersects. Let's assume that there's a charge density sigma. That's the area charge density. Then integral of E dot dA equals Q enclosed over epsilon 0. I'm going to bring this down here. If we chose this Gaussian surface, so this and this are equal distances, and the E fields like this, and the area vectors are in that direction, it adds together. So what you end up with is E times, 2 times E times that area. So EA plus EA is 2EA, and the area of that, I'm just going to put in like that. So that's the flux, 2EA, and that equals the charge enclosed, which is just sigma times the area over epsilon 0. When you solve that for E, the areas cancel, boom, boom, and you end up with 2 sigma, look at my 2, divide by 2, sigma over 2 epsilon 0. But I mentioned that if we just look at a positive charge, we have that E field, and then we add the negative charge, we double that. So the E total for a capacitor is going to equal 2 times that, which just ends up being sigma over epsilon 0. Okay, so let's find the capacitance. We found the total electric field. Capacitance is Q over V, and the voltage is just E times D. It's a constant electric field, so we just multiply the electric field times the distance, and we get the voltage. I'm not worrying about the negative or the positive because the magnitude of the voltage is all I'm really concerned about right there. It's not customary to have negatives here or a negative capacitance. I just worry about the size of that change of the voltage there. And by the way, before I go too fast through this, voltage equals negative integral of E dr, and so if we have a constant electric field, we can take that out. It just ends up being ED. Okay, so we know our capacitance is Q over ED, and that's going to be equal to, let's substitute our electric field in there, sigma over epsilon 0 times D. But we can write that sigma in terms of the charge now, and you're going to see this an awful lot. When you solve for the capacitance of an object, you put the charge in, you write the electric field the voltage in terms of Q, so the Q's can cancel out. And what we have here is Q over, sigma is Q over A. That epsilon 0 is still on the bottom there. You can see I redrew some of this because I made a mistake before. The charges will cancel. A epsilon 0 goes up top, and so you end up with epsilon 0A over D. So a capacitor is related to A, the area. If we have more area, we have more capacitance. That makes sense. For a given voltage, we have more room to store charges, if you think of it that way. And it's also inversely related to D. So what we want is a big A and a tiny D. We want these plates to be as close together, and we want these plates to be as big as possible if we want to design a capacitor that can store a lot of charge per unit voltage.